Hey guys, welcome to this session by Intellipaat. Apache Storm is an open source distributed real-time computation system. So where exactly do they use Storm? Twitter uses Apache Storm for its real-time data analytics and its search engine, as well as Spotify uses Apache Storm in its music recommendation engine. So basically, Storm is used wherever there is a lot of data streaming happening. So in this session, we'll be learning Apache Storm comprehensively. And also guys, before moving on with this session, please subscribe to our channel so that you don't miss our upcoming videos. Now let us take a quick glance at the agenda. We'll start off with a quick introduction to Apache Storm. After that, we'll look at Apache Storm's architecture in detail. Moving on, we'll be looking at Storm data model. After that, we'll be installing and configuring Apache Storm. And finally, we'll be creating a topology in Storm as well as executing it using Maven. Also guys, if you want to do an end-to-end training on Apache Storm, Intellipaat provides a complete Apache Storm certification training and those details are available in the description. Now let us begin this session.
Apache Storm is a distributed and fault-tolerant real-time computation system. Now when we say distributed, it means it works similarly to the MapReduce paradigm, where the processing is distributed in multiple nodes which are running in parallel so that high throughputs can be achieved. Fault tolerant because it can actually work on a reliable stream of data, which actually can recover the data even if the connection is lost. Also, this is a real-time computation system because unlike Apache Scoop, which actually runs on a given scheduled specified time to connect to RDBMS and fetch the data, Apache Storm is something which can pick the data as and when it is created. So we can safely say that Apache Storm is something which is an activity-bound ingestion engine which actually receives the data as it is created and uploads it onto the HDFS or other target systems. Apache Storm originated at Bactype and Twitter. Twitter has a huge role to play because they had a very large amount of data which was streamed through the internet in the form of tweets. They had to actually had the data in near real-time scenarios, process it as it arrives, and store it in their Hadoop cluster. The existing mechanism, for example Apache's Scoop and as well as Flume, was something which was deemed inefficient for their use case. So Apache Storm went ahead and created the Storm libraries, which actually was an activity feed and can pick the data as and when created. In late 2011, the Apache Storm was made open sourced and it actually went as an Apache incubation project. Storm is a distributed real-time big data processing system. It is designed to process vast amount of data in a fault-tolerant and horizontally scalable method. So, if in today's day you are actually talking about X amount of data and you are using, say, 100 machines to cater that amount of data, if your data grows twice in size, you can easily scale your architecture or your cluster to 200 nodes, which is twice the size of the existing 100 node cluster, and you can scale up to actually ingest almost double the amount of the existing data and hence keep your architecture in sync with the growing needs of the processing power. It's a streaming data framework that has the capability of highest ingestion rates. So as I discussed a couple of minutes back, that Apache Storm is an activity-based ingestion engine, and as and when an activity is triggered or happens, the data, whatever is generated, can be actually ingested and stored into the target systems. Doing this, it actually ensures that it can achieve very high ingestion rates as it is horizontally scalable and as well as very fast. Though Storm is a stateless technology, it manages the distributed environment and cluster state via Apache Zookeeper. The Zookeeper takes care of the master and the slave nodes and makes sure that they are running in tandem and without any issues. We are going to discuss about the role of the Zookeeper machines and the master and the slave nodes in the upcoming slides. Storm is very simple and you can execute all kinds of manipulations on real-time data in parallel. That is, as and when the data is received through any streaming engine, for example ZMQ or Kafka, we can receive the data, process it as it is arriving, and then can actually store the data into the target system.
Okay guys, a quick info. If you want to do an end-to-end certification training on Storm, Intellipaat provides a complete certification training on Storm and those details are available in the description. Now let us continue with this session.
This make our processing very near real time. Let's go ahead and have a look into the Storm architecture. The diagram that you are seeing in this particular slide talks about two separate phases in which we have the first phase, which is, you can say that, the master node or the master machine, and then according to the requirement we can have n number of supervisor nodes. You can see that the master nodes and the supervisor nodes are actually taken care by the zookeeper service, and it maintains the state of both these machines. A master node, as it is in the case of our Hadoop architecture, is similar to a name node or a resource manager, which are actually the master nodes of our Hadoop cluster, and actually take care of what task is supposed to be performed by the worker nodes. The master node has a process running on it which is called Nimbus, and all the worker nodes have their individual and independent supervisors processors running on them. Each supervisor process can have spouts and bolts that you can see in the right hand side of this diagram, and we are going to discuss about spouts and bolts in detail in the upcoming slides. So this is essentially a master-slave architecture where the master node running a Nimbus service is going to control the execution on the worker nodes which have each and individual supervisor processes running. The master node is responsible for assigning the work, is responsible for monitoring the work which is assigned to worker nodes, monitor the execution state, and then retrieve the results from them. On a Hadoop cluster, we essentially run MapReduce jobs, while in Storm cluster, we run topologies. So we can say that the Storm jobs are called as topologies. The biggest difference is that the MapReduce jobs starts, they process the data, and they ends eventually when the data to be processed is finished. On the other hand, topology is one started and is intended to keep on processing the live data forever, which it keeps on getting from the data sources like ZMQ or Kafka. The only situation where we can actually see a topology being terminated is either we killed it manually or actually it is disturbed or killed due to some system issues. As we have already discussed, there are two kinds of nodes on a Storm cluster which are similar to Hadoop. We have the master nodes and we have the worker nodes. And the architecture is pretty much similar to the master-slave architecture that we have seen in our Hadoop cluster earlier. The master nodes runs a daemon called Nimbus, as it is discussed a couple of minutes back, which is similar to Hadoop's resource manager. Nimbus is responsible for distributing the code around the cluster, assigning tasks to the machines, and monitoring for failures. Also, apart from the master machines, we have n number of worker nodes depending upon the requirement of the cluster. Each worker node runs a daemon called the supervisor. Each supervisor can run one or more worker processes which are separate JVM processes on its node. They are something comparable to, for example, the node manager services running on the slave nodes in Hadoop cluster can have multiple containers. Each worker process in itself can run one or more tasks in parallel. We can categorize them as spouts and bolts, and we will discuss about the details in a short while from now. So, each worker process can have multiple processes running, and the single supervisor is going to take care of them, which essentially are the JVM processes running parallelly on the same machine. In turn, each JVM process or the worker process can have multiple tasks in the form of spouts and bolts. Each supervisor listens for the work assigned by the nimbus to its node and starts and stops the worker processes as necessary. Please mind you that nimbus is the daemon or the process which is running on the master node. Also, each worker node process executes a subset of a topology. A running topology consists of many worker processes spread across many machines. Moving ahead, let's have a detailed discussion about spouts and bolt. Spout is a source of data stream. It can be unreliable, for example fire and forget, or it can be reliable, which can replay the failed tuples later on when the system turns on. Let's take an example. For example, the Twitter API can emit a stream of decoded URLs, and the Twitter API has a lot of tweets which are actually created or generated by millions in numbers in a given amount of time. There are around 400 million active users on Twitter across different time zones, and the data or the tweets which are posted onto Twitter never stops theoretically. The data, for example, which is generated can be taken from the Twitter APIs and can be stored in the target system. The stream of the tweets which are going to be received can be termed as a spout. Now, in the diagram, you can see that the spout is actually pointing to a bolt. What is a bolt? A bolt is a consumer to the data generated by the stream. Or you can say that the bolt is the consumer to the spout. A bolt consumes one or more streams and potentially produce new streams of its own. In the second diagram, you can see that a spout is actually feeding the bolt 1 and the bolt 1 in turn is feeding the bolt 2. The bolts can do anything from the running functions. It can filter the tuples, it can perform joins, it can talk to database, it can actually create any derived columns, and many more operations are something which are feasible there. The complex stream transformations often require multiple steps, and thus we actually have the requirement for multiple bolts. For example, I am going to have the input from a given spout or a stream. Take example of a Twitter API. This data will be fed to bolt 1, which will process the data in one or the other way. Now let's assume that this data needs to be processed further, and in such scenarios the data will be actually fed to another bolt. You can actually correlate these to chained reducer, in which the data is fed from the mappers to the reducer, and if required, another reducer is called upon the data which is going to be generated from the reduced task. Hence, the chained reducer is pretty much analogous to multiple bolts running in stream and in sync. We discussed that a bolt can actually consume one or more streams. If we talk about stream, this is the core abstraction in Storm. A stream is an unbounded sequence of tuples. When we say unbounded, it means there is no limitation to the data which is generated via a stream. I will reiterate the example of the Twitter API which we discussed a couple of minutes back. As we discussed earlier, Twitter has around 400 or 500 million odd users which are split across various time zones. Most probably every time zone which is possible on this planet Earth. These users are live and posting tweets according to their time zones, and hence Twitter is an entity which is running 24/7. It creates tweets, it creates chats, and it creates different kind of direct messages 24/7, and hence the supply of the data from the Twitter API is unbounded and is actually real time. Storm provides the primitives for transforming such a stream into a new stream in a distributed and a reliable way. So we can actually have the data from a spout or a stream. We can feed it to a bolt, which is actually a processing logic. And if required, this bolt can actually feed another bolt for further round of processing.
Okay guys, a quick info. If you want to do an end-to-end certification training on Storm, Intellipaat provides a complete certification training on Storm, and those details are available in the description. Now let us continue with this session.
For example, we may transform a stream of tweets into a stream of trending topics. So if you are actually avid users of Twitter, and if not avid, even if you have logged into Twitter and have seen the graphical user interface of the Twitter website a bit keenly, you might have seen the trending topics on the Twitter website. Now, how do they calculate the trending topics? Twitter receives the stream of the tweets from different users across the globe. They club them together, and as and when they are arrived, they calculate the count of the hashtags or the buzzwords. Whatever hashtag is repeated most number of times tend to be a trending topic, and the top 10 mentioned hashtags or the words or the buzzwords actually are the most trending topics or the top 10 trending topics. The basic primitive of Storm provides for doing stream transformations are spouts and bolts, as we have discussed in the previous example. So the stream is a spout and the processing algorithm on top of it is a bolt. Spouts and bolts have interfaces which we may implement to run our application specific logic. And as discussed earlier, a spout is a source of streams. Topology is another interesting aspect in the Storm architecture. Topology is a network of spouts and bolts. So we have discussed that spout is a stream or an unbounded supply of tuples or data, and bolt is a way to process. Topology is a collection of both these things, or you can say that a workflow. Earlier we have already discussed that topologies are analogous to the MapReduce jobs in Hadoop. And the difference between a topology and a MapReduce job is that the MapReduce job is kicked off on a given point of time. It processes the data which is given to it, and once the data it is supposed to process is finished, the MapReduce job also finishes and it terminates. On the other hand, topology is something which is eternal and will keep on going until and unless it is manually killed or there is some system specific issue which actually result in its termination. It is a graph of computation consisting of spouts and bolts, so there will be an input in the form of spout and there will be some processing logic in form of bolt. Spouts as data stream source tasks and bolts as actual processing tasks. In a topology, spout will act as the data receiver from the external sources and creator of streams for bolts for actual processing. So if I may reiterate the example of Twitter, the Twitter API is going to publish the data. The spout will be the receiver for that published data. It will pick up that data, receive it from the Twitter API, and create a stream, or you can say that unbounded supply of tuples or data for my processing paradigm or processing logic, which is called as bolt. The bolt is something which is actually responsible for the actual processing or the business logic required to be applied on that given stream of data. The bolts can be chained serially or in parallel depending on what kind of processing we want to do. And the analogy that I have developed in the previous example was something similar to a chained reducer. So as and when required, if I'm going to receive some data from a spout, it will be processed by bolt number 1. And if I need some further processing on that particular data, I will be feeding that data to another bolt, and that bolt will receive the output of the first bolt and will process the data and will write it further. The output from the second bolt can again be the input to another bolt, or it can be the final output that I want to write to my destination system. Moving ahead, let's take an example of a topology. In this particular diagram, you can see some blank rectangles and some blank ellipses, which are connected by some arrows. The rectangles which are here in the picture are the spouts, and they are actually the receivers of the data which are going to be published. The spouts will receive the data, and the arrows from the spouts actually signifies the stream of the data which will be actually the input to the bolts. Now in this particular case you can see that spout 1 is writing to bolt 1, bolt 2 and bolt 3. Also spout 2 is writing to bolt 3 again. For the input from spout 1 to bolt 1 and bolt 2, which are running in parallel, both of them are doing some sort of processing, and then they are writing again as an output to bolt 4, which will receive the processed data from bolt 1 and bolt 2 as its input, and will again do some transformations on top of it. Bolt 3 receives the data from from spout 1 and spout 2, and will have its own separate business logic to be implemented there. We can actually call bolts as the functions which are applied on the incoming data. The collection of spouts and bolts forms a DAG, or what we call as a direct acyclic graph. A direct acyclic graph is a combination of multiple events running in serial or parallel as the business logic demands it to be. Also, multiple modules from this particular DAG can be connected to each other to actually satisfy the business need. Now actually let's go ahead and let's try to derive a relation of topologies to functional programming, referred to as FP in this particular slideshow. We discussed that the bolts can be actually characterized as functions. Now in this particular case, I'm going to concentrate upon one stream of data, which is like the data is received by spout 1, is written to bolt 1 and bolt 2, which will process the data parallelly according to the business logic defined there, and will then actually output the data to bolt 4, which will again further do any processing on top of it. If I want to draw an analogy to the functional programming, I may say that the data is on the spout side. The spout will read this data and will send it to bolt 1 and bolt 2, which are applying functions f and g respectively on the data. They will write out the data after applying functions f and g respectively to bolt 4, which in further will actually apply function h on the already transformed data to derive the business logic out of it. So the DAG in this particular case may look like, first of all, function f on the data that I'm going to receive, function g on the data that I'm going to receive. Bolt 1 will actually perform function f on the data, and bolt 2 will actually perform function g on the data. And the output that I'm going to get from these functions or bolts will be further processed by function h, which actually is implemented in bolt 4. So this way I can actually relate my topology to a functional programming paradigm, where I can actually represent my execution logic or bolts in form of functions, and here is a best example to demonstrate this in detail. Talking about topologies, let's go ahead and take our time to discuss about the different topology patterns available in Storm. We have 7 major topology patterns available in Storm. The first one is streaming joins. The second one is batching. The third one is basic bolt. Fourth one being in-memory caching plus fields grouping combo. The fifth one streaming top n. The sixth one time cache map for efficiently keeping a cache of the things that have been recently updated. And the seventh one can be coordinated bolt and keyed fair bolt for distributed RPC. Let's go ahead and discuss about these topology patterns in a nutshell.
Okay guys, a quick info. If you want to do an end-to-end certification training on Storm, Intellipaat provides a complete certification training on Storm, and those details are available in the description. Now let us continue with this session.
First of all, I'm going to take up the joins, also called as streaming join. A streaming join combines two or more data streams together based on some common field. Whereas a normal database join has finite input and clear semantics for a join, a streaming join has infinite input and unclear semantics for a join to be actually defined and executed. The join type will vary as per the application and as per the business need. Many applications join all the tuples for two streams over a finite window of time, whereas other applications expect exactly one tuple for each side of the join for each join field. As I already said, that the type will vary as per the application, and the practical implementation in detail will be covered up in upcoming sessions. Other applications may do the join completely differently, and they can have some other sort of implementation logic to be defined there. Moving ahead from joins, the second topology pattern that I have is batching. Many times, for efficiency reasons or otherwise, we may want to process a group of tuples in a batch rather than individually. The most common reason that I can think of is an overhead. For example, if I may say that I have 5 persons in a room and I want to serve all those 5 persons with a soft drink. I can have two approaches for that. The first approach can be that I go to the room and I ask the person one that, do you want a soft drink? The person replies that yes, I need a cola. I went back, did the processing, which is getting the cola bottle for that guy, went back into the room and served the cola to him. Subsequently, I reach out to the second guy and ask his preference. After knowing the preference, I went back, get the desired beverage, and then served the person too. And so on, I did this for all the 5 persons each and every time. This is a streaming implementation of the events, and in this case, processing all the requests individually might be a lot inefficient, because in this case I need to go back again and again for all the requests I'm going to have for the beverages. The best way to do this will be the second approach, which will be something like I'm going to ask all the 5 persons about their beverage preference and will note it down. Once I have the beverage preference for all of them, I can go back, have all the beverages at once, and can serve them in a go. This is a batching way of doing the transformations, and this is the second topology pattern that we are discussing. Another example is, for example, you may want to batch updates to a database or do a streaming aggregation of some sort. If you want reliability in your data processing, the right way to do this is to hold on to tuples in an instance variable while the bolts wait to do the batching. So until and unless I have all the desired tuples for the aggregation, I can actually club them in the stream and then can serve to the bolts for all the batching processing. Once we do that, the batch operation, you can then acknowledge all the tuples you were holding on to. If the bolt emits tuples, then you may want to use multi-anchoring to ensure reliability, and it all depends upon the specific application. So the implementation will again vary as per the use case in the batching topology pattern as well. The third and the most basic, as the name suggests, is basic bolt. Many bolts follow a similar pattern of reading an input tuple and emitting 0 or more tuples based upon the execution logic that we are going to perform on that. Once the execution is performed, we can then go ahead and do the echoing that input tuple immediately at the end of the executed method. Bolts that match this pattern are things like functions and filters. For example, I have 1 billion records in a particular data set. Or you can say that I'm going to receive 1 billion records in a given stream. What I want to do is, as and when I receive those tuples, I want to check the age column from that tuple to see if the age is less than or equal to 25 or is it greater than 25. If the age is less than equal to 25, I'm going to filter them out because they are not eligible for the use case that I'm going to apply. But if the age is greater than 25, those are the persons that I am actually interested in, and those tuples I want to store or process as and when required. That is a simple example of a filter function, and this implementation is the simplest example of a basic bolt. This is such a common pattern that Storm exposes an interface called iBasicBolt that automates this pattern for the user. The next implementation that we have is in-memory caching and fields grouping combo. In this topology pattern, it's pretty common to keep cache in memory in Storm bolts. Caching becomes particularly powerful when you combine it with a fields grouping. Let's take a simple example. Suppose you have a bolt that expands the short URLs, for example bit.ly, t.co, etc., into long URLs. You can increase the performance by keeping an least recently used cache of short URLs to long URLs expansions to avoid doing the same HTTP request over and over again. This way, keeping the things in cache, we will request a round trip to the HTTP server and will save a lot of time while expanding the short URLs into long URLs. The fifth one, and the last that we are going to discuss in this example, is streaming top N. We discussed about an example where Twitter actually streams a large amount of tweets from its millions of users across the globe, and it processes them, calculates the hashtag, and based on it actually derives the trends. A common continuous computation done on Storm is a streaming top N of some sort. Suppose I have a bolt that emits tuples of the form value and count. Now we are heading in the direction of the trend setting. And we want a bolt that emits the top N tuples based on the count. The simplest way to do this is to have a bolt that does, first of all, a global grouping on the stream, maintains a list in the memory of the top N items. This approach obviously doesn't scale to a large streams since the entire stream has to go through one task. A better way to do the computation is to do many top N's in parallel across partitions of the stream and then merge those top N's together to get the global top N. If we can actually revisit our previous slides where a particular spout was writing to multiple bolts to actually process the data, we can actually correlate this example with the Twitter implementation of the top trends, top N trends, or you can say the top 10 trends. In that case, the stream is going to be created by the spout and the data is going to be written to multiple bolts as and when they are required. Multiple bolts will actually process the data, which will be something like function f, and they will actually club them together to find the top N records or top N trends or top N tuples for each one of them. Once they are done calculating the top N trends, we can write all of them to a single bolt again, which is going to take the top N records, club them together and give us the top N trends. This is a far more efficient way of actually doing a streaming top N implementation of this example, which in this particular case is the Twitter API example. Let's go ahead and discuss about installation and configuration of Apache Storm on a standalone Linux machine. Let's go ahead and discuss about the prerequisites first. The first and the foremost prerequisite that we have is a Linux or a Unix distribution. In this video, I am using Ubuntu 14.04 long-term support, but any other distribution of choice, for example, Red Hat, CentOS, Fedora, or macOS, which essentially is Unix-based, are fully qualified to be used as the base operating system. The second and the most important prerequisite is having a JDK on the machine. The Java development kit is mandatory, and any of the JDK version 7 or 8 are fully compatible with the latest Apache Storm version. The third prerequisite that we have handy is Zookeeper, which is required for maintaining the state and hence needs to be configured before Apache Storm can be configured on our machine. So these are the three things which needs to be installed before we can do anything with our Apache Storm distribution. And now I'm going to discuss about the installation steps from a Hawkeye view. First of all, we need to download and install JDK. Then we need to download and configure Zookeeper. The third thing is to download and configure Apache Storm. The fourth thing, when we are done with configuring Apache Storm, is to start the services Nimbus, Supervisor, and UI. Nimbus is the master server. Supervisor is the slave equivalent of a process, which is responsible for running the spouts and the bolts. And UI is the web UI where we can actually verify our topologies which are running on Apache Storm. We are going to discuss about the web UI later on. And then the last step, verify the configuration by looking at the web UI at port 8080. Okay, so let's go ahead and start with installing JDK, the first prerequisite. I am assuming that you have a running version of any Linux distribution discussed above and they are up to date. So I'm starting with installing JDK. So we discussed about a bunch of Linux distribution above, and we discussed that we can actually use Ubuntu, which is the Linux distribution in this example, or we can use any of the Red Hat Enterprise Linux or Fedora or CentOS or any RPM based Linux distribution for that matter to actually go ahead and get started. As the underlying structure for these type of distributions are different, the commands are going to be a bit different, and on whatever version of Linux or whatever distribution of Linux you are working with, you'll be comfortable using the commands there. Just for the clarity, I have mentioned the commands to install JDK on Debian based and RPM based Linux distributions separately. So because this is Ubuntu 14.04 and this is a Debian based Linux distribution, I will be using the apt-get repository to install OpenJDK version 7. To do this, let's go to the terminal and fire the command to install JDK. So I'm using sudo apt-get install openjdk-7-jdk. I have JDK installed already in this machine. So running this command will ask for the password, and after running this, it's just asking for just 3 upgrades. For you, that will be just a bit higher. We'll be asking for installation. Click on yes or type Y, press enter, and it will start the installation. It'll be just a couple of minutes before the JDK is installed, right? And the next step for us will be to download Apache Zookeeper from the Apache's mirror. Also, we need to have Apache Storm downloaded. So to do that, you can simply scroll onto web, and because these are the freewares, you can simply Google download Apache Zookeeper. So we have this zookeeper.apache.org and release. The website should give us the link for downloading it. Click on download and it is again giving us the link to Apache Mirrors. Following the links, we should be good to go ahead and access one of the Apache Mirror having the Zookeeper binaries available there. So there'll be multiple versions of Zookeeper available and you can select from this stable directory to go ahead and download the latest stable release, which is 3.4.8. In my case, I already have downloaded Zookeeper. For you, you can just simply click on this particular link and download Apache Zookeeper. Similarly, we need to download Apache Storm, and googling Apache Storm is going to get us to this Apache link, which actually has Storm hosted. So we have the download button here. Clicking on it is going to give us the options that which we need to download. So the current 1.0.x release is 1.0.1 and we are going to download the first one, the Apache Storm 1.0.1.tar.gz. This is a pre-compiled version of Apache Storm and we have the zip version as well as the source codes as well in tar and zip version. So clicking on this link is going to actually give you the link for the Apache mirrors. Clicking on it is again going to land you to the download for Apache Storm 1.0.1. So I already have Apache Storm 1.0.1 downloaded, and for you, if you do not have it already, you can just simply click on this link, and as you can see that the archive size is something around 162 MBs. Okay, I'm going to click on cancel because I already have the setups downloaded with me, and these were actually just the steps to actually go ahead and download Apache Zookeeper and Apache Storm. Okay, so I am closing the browser now and looking at the terminal, just like under a minute, which is left for my JDK to be configured. In the meantime, I have my Apache Storm and my Zookeeper on my desktop, and I'm going to go ahead and configure them on my machines. Okay, so the first thing before I can actually go ahead and configure Apache Storm, the first thing is Apache Zookeeper. So for me, I am going to double click on this tarball, right, which actually has this Zookeeper directory. I'm going to click on extract and I'm going to select home and extract Apache Zookeeper there. Please be noted that you can extract the tarballs at your directory of choice. I am doing it on home because it's pretty easy to access, and for my sample configuration I tend to do that. Okay, let's click on extract, and in a couple of seconds I should have the extraction completed successfully. Alright, if I go to home, I have this zookeeper-3.4.8 directory created, where 3.4.8 is the version, right? Double clicking on it is going to show me the different directories and the files which live in there, right? The first and the only thing that I am supposed to be bothered about Zookeeper is having the configuration file set up. So if you go to the conf directory from Apache 3.4.8 into this conf directory, right, you can see 3 files present, and the file of interest in this particular case is zoo_sample.cfg. Let's copy and paste, create a new file, and I'm going to delete the copy and the sample thing and create a new one, zoo.cfg. So cfg is like configuration file. Let's click open with gedit, and then I'm going to see different options which are listed there. I'm not going to play with the options as of now, right? The data directory is something that I can change accordingly. Now, for example, in this particular case, the first property that I can see is tick time. Now, this tick time has a value of 2000, and they are the number of milliseconds before the zookeeper picks up the states and update the states on this particular data directory. Okay, so by default it is /temp/zookeeper, and what I'm going to do, I am going to place this data directory on my home directory /home/user/zookeeper. Now this directory is not going to coincide with my zookeeper 3.4.8 directory, and a new directory will be created once I start my zookeeper process. So changing this to something which is more relevant, /home/user/zookeeper is the only change that I'm making, and I'm leaving it to run at the port number 2181, which is by default. Okay, so I'm going to save it and I'm going to close it. All right, and that's the only change pretty much that I have. So please reminding you once again, copy this zoo_sample.cfg, create a new file and rename it to zoo_cfg, and change that data directory destination to wherever you want. Even if you want to leave it that as the default value, you can simply ignore this and can leave it as it is. But having the data directory at a known position can actually give you the insight into the logs generated by Zookeeper later on. Okay, so that is the only thing that I was going to configure in Zookeeper configuration, and I am done with configuring Zookeeper here. Okay, and in the back end, my JDK has been installed. So I have installed JDK7, Open JDK7 in my Ubuntu 14.0.4. Okay, so by default, when I use the command line option of configuring JDK, the installation and happens at user lib jvm, right? So if I go to the cd/user/lib/jvm, do an ls on top of it, I can see the directories which are created. For example, there's java -7-open-jdk. I'm going to copy it up, do a cd on top of it, do a listing, and I can see that all the directories are in there. Cd bin listing, so all the things are in there. All right, that's cool, that's great. Okay, so I'm going to exit it as of now. Click on cd, that is it. So java is configured. We are going to take a note of this openjdk configured later on when we are going to configure our bash rc. So we have also downloaded Apache Storm 1.0.1, the tarball, right? As the configuration change that we did with Zookeeper, we are going to extract the Apache Storm tarball onto our desktop, onto our home directory in this particular case. Click on extract, and in a couple of seconds, I should be good to go. Looking at the home directory, I have this directory created Apache-Storm-1.0.1, where the last part of the complete name is the version number. So the naming convention is Apache-Storm- the version number. Okay, so Apache Storm 1.0.1 is the directory which is created right now. I'm going to go inside this directory and see what all do I have. So there are a bunch of directories in that, and I am rather concerned about this directory, which is the conf directory in this particular case. I have 3 files in this, and the storm.yaml file is something which actually hosts the properties and is the file of interest in this particular case. So just simply right click and to open with the gedit. There I can see a lot of lines and every one of it is commented out. So the first character for every line is a hash or a pound sign, and actually it signifies a comment in uh, 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 in the Unix environment. All right, So there I can see this comment that these must be filled in for a Storm configuration, right? So what I'm going to do is, first of all, let my configuration know that where my zookeeper servers are. So I'm going to uncomment these two lines, okay, and I'm going to replace server 1 with localhost. Please mind you that this is a standalone machine, okay, and the zookeeper configuration that I just did is on localhost. All right, and I'm going to leave the server 2 as commented out because I have a single zookeeper instance running on localhost, and that is enough for me. And I'm going to uncomment this line nimbus.seeds. Please be known about this fact that Nimbus is the master node of Apache Storm. So nimbus.seed, so it is asking about how many different hosts that I can have, and if I have like more than 3, I can simply separate it with a stick and start like the fourth host here, but never mind, that is something which is there for distributed environment. In this particular case, I'm going to go ahead and write localhost in double text, save it as it is, and the only two changes that I need to make: uncomment the lines and actually replace server 1 with localhost and host 1, host 2, host 3 with localhost in nimbus.seeds. Alright, once done, save the file and close the file. Okay, that was pretty much it, and that was the only change that I wanted to do with my Apache Storm tarball, as it is mentioned here. Okay, now once it is done, what I need to do is I need to actually update my bash rc file for the newly configured tools. So any one of you who has worked with Linux might have came across this file .bashrc. Anyone who actually hasn't, and if got a chance to work on Java in Windows, this is something that we did via after installing JDK and setting the environment variables. So bashrc is similar to actually updating the environment variables in Windows. Okay, so just to make sure that you should be on your home directory before you go ahead and start configuring your .bashrc file. In order to do that, just to make sure, press cd, press enter. That will make sure that whatever directory you are in, it's going to bring you to your home directory. EW is going to show me yes, I am at /home/user. Okay, now I'm going to do sudo gedit bash rc. Okay, in the bash rc I have already furnished the directories, and please be noted that the directories are going to be different for each user. Now in this particular case, I said that export storm_home is equal to /home/user/apache-storm-1.0.1. So this directory path, if you remember, we extracted our tarball at the home directory, apache-storm-1.0.1. If I right click on this one, click on properties just to see, so if I can see that this is living on /home/user, and the actual directory name is apache-storm-1.0.1, and the path name goes in sync with that. Storm_home is equal to /home/user/apache-storm-1.0.1. Similarly, I'm setting the java_home, which actually is living in /user/lib/jvm/java-7-openjdk-amd64. Please be noted that the Java path may differ for each one of us according to the Java version that we are going to install and the Linux distro that we are working on. After creating these two variables, we need to add these variables to the actual variable or the main variable, which is called as path. So I'm saying export path equal to $path colon, which is actually separating two separate variables here, $java_home/bin. And after that, I am actually adding the second variable as well, which is $storm_home/bin. Please be noted that the order is something which actually do not impact the overall purpose, and java underscore home or storm underscore home can be actually interchanged in the position. It's not going to impact our use case at all. So let's save this file and close the gedit, and let's get back to terminal. So once the bash rc file is uh, updated, what we need to do is either we should reload the bash rc with the dot space dot bash rc, right? Or as a simpler approach, we can close the terminal and we can launch the terminal once again. Okay, so there we are. So we have as of now installed JDK, we have downloaded Zookeeper, we have downloaded Apache Storm, and we have configured pretty much them up to the mark as of now, extracted them onto our home directory, created some variables on uh, in the .bash rc file. Okay, the next thing in line that we are going to do here is actually first of all start the Zookeeper service. So in order to do that, I will be going to the Zookeeper directory, 3.4.8, that's the directory that I'm talking about. Okay, and inside that I am going to go inside the bin directory. Doing an ls in this directory, you'll see that you have various scripts available, and the one that we are going to use in this particular case is zk server.sh. So this is zookeeper server.sh, and it is going to start the service for us. All right, so let's go ahead and start the zookeeper service dot slash. It means that this is in the current directory, and I'm going to execute it and start. All right, so it says that starting Zookeeper and the service has been started. Going to the home directory once again, I can see that the directory which I have mentioned as the data directory for Zookeeper has been created now. So Zookeeper is the new directory that I can see here. So it is going to be updated. We're not going to discuss about this Zookeeper directory in detail, but just to let you know that the data directory that I had changed in my zoo.cfg configuration file has been created once I started my Zookeeper directory for the first time. Alright, so the Zookeeper service has been started and it is going to take care of the state of my Apache Storm configuration. Alright, so the next thing that I'm gonna do is first of all, let's clear the screen, press a CD, and now I'm going to go inside my Apache Storm directory. Here I have the bin folder again. Doing an ls on top of it, I can see this Storm listed here. All right, so this Storm file is present with me, right? So I'm going to use the same nomenclature or the syntax again, dot slash, and execute this Storm command along with different options that it expects. So first of all, I am going to execute Storm command with the option Nimbus. As we have discussed that Nimbus is the master process and is the daemon or the process which is running on the master machine and is going to take care of all the execution and will submit the work or will instruct the slave nodes to do the work. So let's start this service. It will take a couple of seconds. So in the meantime, I am going to open a new tab. Okay, and there I'm going to start. So see, I'm still inside this Apache Storm -1.0.1 slash bin directory. So I am going to use the Storm command again, and I'm going to use supervisor simultaneously. So looks like okay, this has started. Let's click on enter. So service once running on your terminal will keep on running, and you need to kill it manually. So I don't want to kill it as of now, so I left it as it is and went to another tab where I started the Storm supervisor. Now I'm going to open a third tab, and there I'm going to do Storm, and I'm going to initiate the UI. So UI is the user interface, as we have discussed. All right. And once this is up and running, the next thing that we are going to do is go to the web interface, the user interface of Apache Storm, and verify that each and everything is running fine for us. Okay, so looks like this has initiated as well. So I'm going to go to the Firefox web browser, and I'm going to mention localhost because I have configured Apache Storm on the local machine. So localhost will be the host address. If that had been a distributed environment, localhost would have been replaced with the IP address or the host name of the machine where the Nimbus daemon is running, or you can say that the host name or IP address of the master machine. So I'm going to go to localhost, and then I'm going to choose 8080 as the port where the Apache Storm service ran by default, and you can say that, which is the UI port of Apache Storm. So let's click on enter, just give it a couple of seconds, loading summary. So if you can see that your page is running just fine without any issues, right? It's like pretty much surety that your Storm has been configured correctly. So here you can see in this particular case version is 1.0.1. You have one supervisor and you have 4 free slots. Total slots are equal to 4. Okay, so they are the Nimbus summary. Okay, the local host, it tends to be offline. Okay, but this Ubuntu, the user is the leader as of now. The version is 1.0.1 and it is up since last 2 minutes and 1 seconds. And all that time I was doing that talking. So there is this summary of the supervisor. The host is Ubuntu again, and it is up since last 1 minute and 26 seconds. And there is a version of this particular machine. All right, and there are some configuration properties which are mentioned below. Just in case, if I refresh this page, reload it again, and now you can see that the 2 minute 1 second has updated to 3 minutes and 9 seconds, and similar is the case for my supervisor. So looks like everything is pretty much fine. My supervisor and the Nimbus daemons are running, and it marks that my Storm uh, is running up and fine on my local machine. So this marks the end of this lecture, and we have successfully configured our machine to execute Apache Storm or run Apache Storm. So just a quick recap, right? So the prerequisite was like having a Linux and Unix distro and installing JDK and configuring Zookeeper. So we were working on Ubuntu 14.04, and I downloaded and installed the JDK on it, downloaded and configured Zookeeper, and I downloaded and configured the Apache Storm tarballs, and then I followed all those steps to the glory, I will say, which configured all the processes and all the prerequisites and the main components successfully. And we were able to verify the configuration by looking at the web UI of Storm at 8080 port of our localhost machine, because localhost is the master daemon in this particular case. Let's go ahead and discuss about how to create a topology and execute it using Maven. So let's get started. We have a bunch of prerequisites and they are notable and very important. So these are, first of all, we need a JDK installed in whatever operating system we are trying to execute our topologies. Second, we should have Maven installed on the operating system. Third, we need a text editor, for example, Notepad, or we can use any integrated development environment or IDE in short, for example, Eclipse. In this tutorial, I am going to use Eclipse as well as the Notepad editors to actually accomplish the required coding and other stuff. Also, please be noted that the operating system or the host environment that I'm going to use has all the basic prerequisites which were discussed about while installing Storm. So Apache Storm is installed there and all the related dependencies for Apache Storm are already present there. The prerequisites that are discussed here are specifically for the code that we are going to execute. Okay, so without wasting time, let's go ahead and jump start into the coding part. We discuss that Apache Storm execution framework is called as a topology. A topology is a something which actually consists of multiple spouts as well as the bolts. Spouts are something which actually are the inputs, and the bolts, on the other hand, are the processing part of the complete code which is written or the complete project which is created and are called as bolts. The complete collection is called a topology. To accomplish the example that we are going to discuss, we will be using a Maven project. There will be some dependencies about which I'll be discussing, and I'll be discussing about the pom.xml file which will take care of all the dependencies. Okay, so the first stepping stone that we have is creating a new Maven project. I will show you how actually we can do that and also all the other things that I'm going to discuss in the slideshow. But let's first of all see the theoretical aspect of these things. So first of all, I need to create a Maven project, and I need to add the dependencies because this is a Storm topology and you must add a dependencies for Storm components. There will be some jar files, some classes which will be used at the backend, and this dependency addition is going to take care of it. As you can see in the following lines, you can depict a opening and closing tag of dependency, which actually is adding a group id org.apache.storm, and the artifact id is storm core. Looking at this dependency, we can easily figure out that we are actually talking about the Storm core jar, which is going to have all the basic required class files for our code to execute. Once we add this dependency section to our pom.xml, we actually will go ahead and make some more changes, which will be about actually adding the configuration. So we'll be discussing about adding these configuration lines in detail and hands-on in a couple of minutes. Also, once the dependency is added, we need to go ahead and add the plugins which are discussed in the slides that you are seeing on your desktop. Now, first of all, I am going to use the exec Maven plugin, which is going to help me with the execution using Maven. Third is what is the goal, and which actually states as execution. Also, I am going to add a bunch of dependencies which are going to talk about the class path scope and which main class is going to be used for my execution to start. Okay, so before I go ahead and discuss about the code part, let's actually jump ahead to our workplace and let's do the hands-on upon how to create a Maven project. So I am using this Ubuntu VM, alright, and I'm going to use Java IDE to actually create these Maven projects. I can simply click on here and click on project, and then from the drop down I can select Maven, and from the Maven I can click on Maven project. Clicking on next is going to ask that where I want to store the project which is going to be created, and then the type of the project, which should be actually taken as group id as org.apache.maven.archetypes, and the artifact should be quick start. Clicking on next, we are supposed to give a group ID and artifact ID. For our example, we can take the group ID as Storm topology and the artifact ID can go as word count. The example that we are going to discuss is about word count, and we are going to have some sample input which is going to be processed here. I can see that it says that invalid project name word count because it already exists. For me, I already have a word count project. For you, you can just write word count here and click on finish. Once done, expand this thing and you'll be able to see multiple directories created with the pom.xml file. So while creating the project, we have mentioned a particular directory where the source code should be stored. And let's go on to my workspace, which is on home for me. And this is the directory that I have created with the name word count. It will have three files, or I'll rather say two directories and a file present by default. One is source, one is target, and the third one is pom.xml. So let's go to source, and there we'll be seeing two folders in that which are created by default. One is main and one is test. The main is going to hold the main code for our job to execute. The test directory is supposed to have the test cases. For our use case, we are not going to create any test case. If you simply go to test, you'll see Java, then you will see the actual path which is according to the artifact ID that we have given, word count, and there you'll see if any Java file. Go ahead and delete that because we do not need it. Okay, going back, looking at the main directory, we'll again have the subdirectory structure, and there I have added already four code files which I'm going to discuss with you in a minute. These four code files are my spout as well as the bolts which are required for the execution. So let's discuss about these four Java files and what all these four files do. So in this case, I have four Java files which are there on the screen. The first one is the random sentence spout. We discuss that spout is something which is the stream or the input to our project, which we call as topology in Apache Storm, and bolts are the execution logic which are going to pick up that data and process it up. The fourth file which I'm going to discuss, the word count topology, is pretty much similar to the driver class which is present in our MapReduce codes. Let's first of all discuss about the random sentence spout class which I have created to actually pass some random input data to my bolts which are going to process them up. Please be noted that these four code files I have created in my word counter directory, and when you create your code, you are supposed to create these code files as well, right? So this is a custom code and the programmer needs to do that. I'll be passing these Java files to you so that you can go ahead and start doing the things. Okay, so I am starting with the random sentence spout Java class and I'm opening it with gedit. There is a bunch of dependencies which I'm not going to discuss about. I am going to start from here. So I have a class in this particular case which is called random sentence spout, and actually it is extending the base rich spout class. I am going to create a collector which is going to actually collect the output emitted from my spout. So spout output collector is the class which is going to be used, and an object with the name of underscore collector is one which is going to be used to collect the output emitted here. So if you see, this spout output collector is something which is coming from backtype.storm.spout class. There is a object of class random with the name underscore rand, and it is of not directly related to Apache Storm, but this is something which is there to generate a random number and which is actually available in java.util. Alright, so let's go ahead. So first method that I should discuss about in Spout is the open method. Open is called when an instance of the class is created. So for example, whenever I'm going to create an instance of this particular class, random sentence spout, this open method will be called exactly once. This method actually receives a configuration object, a topology context, and a spout output collector. In this case, I am initiating the underscore collector object of the spout output collector class with the collector which is passed to it from my main driver class, which we discuss about and we are going to discuss in detail later on. And for random numbers, I am just going to pick up any random number as my code is going to be executed. Next tuple method is something that actually behaves as per its name and actually picks up the data and emits the data to the stream. So talking up in this particular case, I am not actually connected to a live stream, but just to make the thing simple for our first example, I have taken up this string having 4 sentences. The first one is the cow jumped over the moon. An apple a day keeps the doctor away. The third one, 4 score and 7 years ago. And the fourth one, Snow White and the Seven Dwarfs. And actually there is a fifth one as well, which is I am at two with nature. So these are just random records which I am going to use, and I've created an array called as sentences, and I'll be picking up these records and will be passing these records to my stream as input just randomly without any logic there. So what I'm going to do, I'm going to create a variable string sentence, and I'll be picking from the sentences array a string from the random index. So I'm going to actually fetch a random number which should be one of the 5 sentences that I have in my array. Now once this is picked up and is sent to the sentence variable, I'm going to use the underscore collector object that I have created above, and I'm going to use the emit method, and I'm going to emit this sentence as the output from the spout. This output from the spout is going to be act as the input to my bolts. There are a bunch of other methods which are there in my spout, but because this is a basic example, I'm not going to discuss about them. One of them is ec, which actually is used to signify the acknowledgement of processing of a particular record. Fail is there when a particular record is received but is not processed upon. And the third one that we have used in this particular case is to declare the output fields. In our case, the output field is sentence, as we have picked up earlier, and declarer object is going to declare that a single field called a sentence is the output from our spout. So what we are doing in this case, I am going to pick up any of this particular record randomly. You can see in here, right? And this picked up random record is going to be sent to the bolts as input using the emit method from the collector object. Alright. Once the random sentence spout spits the data, it is going to go to the split sentence.java class. In this particular case, I have a class which is called split sentence, and it is extending base basic bold class. There is a method which is called execute, and this method is actually called to process the tuples that I'm going to receive as input from my spout. So I'm going to receive 2 arguments. First is the tuple, and the second one is basic output collector object, which is going to be used to collect the emitted output. So here I have created a variable with the name sentence, which is actually being initiated with the tuple that I am receiving as an input from my spout. I am going to create an iterator which is going to iterate on each word present in the input that I'm going to receive. Please bear it in mind that our use case discuss about word count thing, and of course a single record which is an output from my spout is going to have multiple words, and I'm going to create multiple key value pairs out of it. So I'm going to use an iterator which is going to pick each word from the input and is then going to create the different key value pairs for me. Okay, now we have created the boundary object from the break iterator class. Okay, now let's go ahead and give it some input. So I saw that a sentence variable is initiated with the input which my bolt is receiving, so I am actually passing the sentence to it. Now I am starting with the first word and I'm saying that int start equal to boundary dot first. So boundary is actually pointing to the input that I'm receiving and I'm pointing to the first word. And then I will iterate over each word and emit it to the output stream. So int end equal to boundary dot next, and until I have the words in my break iterator class, I will be keep on going, and I am going to actually create a word from the sentence that I have, and I'm going to replace all the white space characters with empty, or you can say that I'm going to remove all the white space characters from the words that I'm going to receive. So I am again going to check that if a particular word is not equal to blank, or you can say that is something which is missing, or if it is not an actual word, then I'm going to skip it up. But if it is an actual word, I'm going to use the collector method, collector object, and I'm going to use the emit method, and I'm going to emit the word as an output from here. And also I'm going to say that the output from this particular bolt for me in this particular case is word. So as of now, what I have done, I have received the input as a complete sentence from random sentence spout.java. The split sentence read that record, break it up into words, and then write it again to be used by my next bolt, which is word count.java. So in this particular case, I am creating a map and the name is count. So I'm creating a hash map which is going to have a key value pair in the form of string, actual word, and integer, which is going to be the actual count. So again, the execute method, because this is again a bolt, right? And I'm going to use the same method which is called execute to execute the input, the tuples that I'm going to receive as input from my previous bolt. Great. So I am going to receive a tuple and a basic output collector again. Okay. I'm going to set a variable called as word with whatever I'm getting from my previous bolt. I'm going to set the count equal to the counts.get word if I already have any count. Else if the count is null, I'm going to set it to 0. Then there'll be an increment which is count plus plus, and then I'm going to use the put method from the map that I have created, and I'm going to add the word and the count in the form of a key value pair, right? And then I'm going to use the collector dot emit, and I'm going to write out the output from here, declaring that the output that I have has two fields. One is word and the second one is count. So I have this stream generated spout, which is going to give me the data, right? The output of this spout is actually used by the split sentence, which is going to pick up each record, break it up into words, right? Process it up, remove any blank spaces, and then going to send it to the word count bolt, which actually picks it up, counts the actual occurrence of that word, and store it in a hash map. The fourth class that I have do not hold any logic, business logic for me, but is rather the driver class kind of thing. So in this particular case, you can see I have the main method from where the execution will start. I have a topology builder class and an object for that class which is called builder. This object will be used to set, first of all, the spout, and then the parallelism for this particular spout. If missing, it is going to be default and it is going to be 1. Then I'm going to add the first bolt. Please pay attention here. So I'm going to use builder.setSpout with the name spout, and actually is a new random sentence spout, which is the first class that I have, and I'm going to use an instance of it. So remember this thing, that this open will be used when an instance of the class is created. So I'm creating an instance of this class, so the open method will be used. Now the second thing is to actually add a split sentence bolt with the name of split, and the parallelism hints that I'm going to have 8 executors, and the operation means that shuffle grouping subscribes to the spout and equally distributes the tuples across the instance of the split sentence bolt. So my spout is going to be the input to my split bolt, which is going to actually perform the shuffle grouping operation, which will group the similarly created similar words together, and is going to use 8 parallel threads there. Once this is done, I am going to add another bolt with the name of count, parallelism hint 12, and the fields grouping subscribes to the split bolt, the second one that I had, and ensures that the same word is sent to the same instance and is grouped together, fields grouping, making it sure, so that I can count them using this count bolt that I have written, right? So create a config object, set the debug to true or false as it is your requirement. If the arguments are not equal to null, and I have some arguments actually present in my input, by default I'll start with 3 parallel workers, which are actually going to be increased and decreased as you can see the hints that I have passed in my spouts and bolts. And then I'm going to use the storm submitter.submit topology method, and I will be sending the topology that I have created just above with the name of builder, and then I'm going to use the cluster.shutdown, which is going to shut down my cluster once the execution is complete. Alright, so let me show you a diagram before we go ahead and execute the complete flow. So this is the diagram which actually discusses about the complete flow. So I have a spout, as I have shown in the figure to you guys, right, which actually has 1, 2, 3, 4, 5 different records with the name the cow jumped over the moon, the apple a day keeps the doctor away, 4 scores and 7 years ago, Snow White and the 7 dwarfs, I am at 2 with nature. Now the input to the next bolt is something which is the output from the spout. As we saw that I had a random object or object of this random class which is going to pick the sentences, or if I rather say the array elements from the array, which is going to hold all these 5 records together, will generate them randomly, and then is going to send them to the first bolt, which is called as a splitter. This splitter, for example, first one is getting Snow White and the 7 dwarfs. Well, pick up this record, will split the words into separate entities altogether, right? And then is going to feed the next bolt, which is the count bolt, right? And which actually is going to receive the output of my first bolt, which is splitter, and is then going to club or group them together. Once they are grouped, is going to actually calculate the total count and then write it out. Alright, so this is the flow. Get the input, split it up in the first bolt. Once it is split up, group the similar words together, send them to the next bolt which is there to count them up, and because they are grouped together, same word, for example snow, if it is existing anywhere in the world, it is going to be there with the worker node which is going to have the ands together. For example, I have an and here in the first splitter, I have an and here in the second splitter. Once shuffled, it is going to be there and the count will say 2. All right, so that is the holistic approach of our code that we have just written, right? So what I'm going to do now is I'm going to go ahead and execute the topology which is just created to see that if we can actually get some output out of it. All right, so let's go ahead and let's head to the terminal. I'm going to use Maven, right, to get the things done. So please first of all be noted that I have started the Nimbus service on my machine, okay, which is the master service. I have started the supervisor service, which is the worker service or the slave service for Storm. I have also started the UI, which is not actually the most important part, but just to see it graphically that how the things are going up, right? Now, after that, I am going to go inside the workspace directory. So just to let you know that here I am, cd slash home user workspace. This is the directory where all the codes from my Java IDE are stored. Inside that I have a word count directory, and if I do an ls here, I can see pom.xml, source and target. So if I go inside source, I'll be able to see all my codes, but the execution should start from that directory where pom.xml lives. So I'm going to use the command which is mvn, which stands for Maven, compile, execute Java, and the Storm topology that I'm going to execute is named as Storm topology.word count. So this will be something that will actually change with the artifact ID that you will name while creating your Maven project. Dot, then you are going to mention the main class, or you can say that the class which actually has the main method. So for our code, the word count topology, let me show you this thing here. So the word count topology uh, code is the one which is having the main method, and where we are actually creating the topology, adding the spout, adding the bolts and other things, and then we are actually using this topology to start the execution. All right, so let's go ahead, let's head to the terminal and use this command to trigger our execution. MVN will take care of all the dependencies that we may have, all the classes which are required at the back end and other things, right? So it will start executing our topology in this particular case. After a couple of seconds, we should be having the outputs from the spout that we had, and the spout should send the data to the bolts should start processing, and once it is done, we should see the output in the form of multiple words which are going to be created. All right, okay, so you if you see this here, so this is a sample output that we are looking into right now, and it is saying that we actually received the message from source, and the spout send this Snow White and the Seven Dwarfs, and then the split received it up, and it splitted the input to separate words, snow separately, white separately, and the seven dwarfs this output then actually was received by the next thing that we had in line. Alright, there you can see actually. So we received, okay, so after the execution went ahead, which is like a fast forward actually, right? So you can see that the spout send this Snow White and the seven dwarfs. Split, the first bolt, received this input, divided it into separate words, Snow White and the seven dwarfs, separate words altogether. Now because this was sent multiple times, what I had and 72 times, dwarves 36 times, the 148 times, snow 36 times, white 36 times. So that is something that I received the output from all the records that I had, and I kept on calculating them, and this is at the end of the day the final result that I have. So this was the first execution that we have, right? And there we have the counts for the different words that we had from our spout. Please be noted that we had the word snow only once in all the 5 words, but the spout kept on iterating randomly and kept on sending the data, so it has actually sent the same record 36 number of times, and the count here is 36. For every snow we had like 2 ands from 2 different words, and I have like 72. Dwarves is 36. The was present in 3 records, and the count actually goes like 148. So that is how the count actually is there for different words altogether. This was it for our sample example.
Okay guys, a quick info. If you want to do an end-to-end certification training on Storm, Intellipaat provides a complete certification training on Storm, and those details are available in the description. Okay guys, we've come to the end of this session. I hope this session on Storm was helpful and informative for you. If you have any queries regarding this session, please leave a comment below and we'll love to help you out. Thank you.